Hello, my name is Ruben Chavez, and I am a graduate student at the University of Illinois at Urbana-Champaign, and I will be the narrator of this video series. This work was supported by the IFAN's Food Microbiology Committee. As discussed in the introduction video, the simulation app gives the user a tool to recreate a desired sampling plan and obtain the probability of detection of a hazard, either pathogens or mycotoxins, as well as the probability of acceptance of the produce field or grain lot. This gives the opportunity for the user to compare different sampling plans and different scenarios of contamination to analyze the best scenario for hazard detection and acceptance of the tested field or corn lot. This video will explain the required inputs for the sampling simulation of a produce field. These inputs allow the user to simulate and compare results of different scenarios, such as implementation of simple random sampling, stratified sampling, or systematic sampling. In addition, the user can simulate different levels of contamination and evaluate how this affects hazard detection and acceptance probability of the sampling plan. For produce sampling simulation, the app requires 15 inputs. For each input, the modeling app will have a specific question that asks the user to fill or choose the desired option according to the intended sampling plan. Some inputs have predetermined values that have been selected according to literature studies, but can be customizable according to the user preferences. The first input is the size of the produce field in meters. The default area of measurement consists of a 1-acre field, which is a 63 by 63 meters. However, you can customize the length and width of your field to accommodate the sampling needs depending on your own farm's reality or your preferred management practices. The next input is the geometry of hazards. This refers to the affected shape of the contamination event. The app has two options: point source or area based. Some common point source contamination scenarios include fecal material found in between the rows or beds due to animal intrusion, fecal material found in between the rows or beds due to the presence of birds, or visible damage to the crop due to animal intrusion. If this option is selected, the user will need to assume how many contamination points are on the field and the radius of contamination of each point. For area-based contamination scenarios, some possible scenarios could be irrigation of the fields with contaminated water, fertilization of fields using improperly composted manure, or proximity of cattle ranching to the vegetable farm. In these cases, contamination is generally uniform throughout the affected area. The next input required are the mean and the standard deviation of contamination level in log CFU per grams. Both can be obtained from previously measured contamination levels or from historical data of microbial load in your field. The background level of contamination refers to endemic bacteria that might be present in soil. In this input, we assume the prevalence of pathogens is close to zero. However, if you previously applied manure or if your field is close to cattle ranching fields or surface water, the likelihood of having detectable levels of bacteria would increase. The user can adjust this level to reflect those scenarios. The expected decay function refers to the concentration distribution of the pathogens inside the contaminated area. The user will have three options to select the contamination distribution of the affected area according to the geometry of the contaminated point. The three options are exponential decay, uniform decay, or Gaussian decay. The exponential decay demonstrates the behavior of the bacterial infection as a function of distance, by showing an exponential decrease or increase of contamination level and detection of hazard as you sample further or closer from the contaminated spot. For example, the farther you are from the fecal pellet from a bird, the concentration of bacteria and the probability of detecting the hazard will decrease exponentially. The uniform decay function is usually linked to a widespread contamination event where the contamination has been equally distributed across the field. such as irrigating the field with contaminated water. In this case, we assume an equal distribution probability of detecting the hazard across the field. The third option, the Gaussian distribution, is a normal distribution. It is similar to the exponential decay in that contamination level and probability of hazard detection decrease as you move further from the contaminated spot, but this follows a bell-shaped distribution rather than an exponential decay, generally more suitable for contamination points with high radius. Now that we have specified the distribution or shape of contamination, the next input allows the user to indicate the rate of contamination decay. The rate of contamination decay refers to the bacterial growth function in the contaminated point or area. The model can accept values ranging from 0.0001, which is slow bacterial growth, up to 0.01, which is fast bacterial growth. The predetermined value of the modeling app is 0.01. Then we have the sampling attribute case. This input is the microbiological criteria recommended by the International Commission on Microbial Specification in Foods for pathogen sampling. For this input, the user can select the sampling case according to the ICMSF recommendations. For zero tolerance organism, the user can select cases number 13, 14, or 15. The next input is the number of sample points. This input refers to the individual samples that will be collected for pathogen detection. If the user's practices are to take composite samples, the user must input the total number of samples that constitutes each composite. For the microbiological criteria, the user can change the values of the microbial limit used in the sampling plan for both lowercase m and uppercase m. The sampling strategy refers to the sampling approach that will be utilized to collect the samples. The app has three options. The first one is simple random sampling, where the sampling points are selected at random and all selections of the field are equally likely to be selected. The second option is stratified random sampling. In this sampling strategy, the field is divided into non-overlapping subgroups and samples are taken randomly from each group. For example, the field could be divided according to their contamination history and perform random sampling in each different area. This method is a good choice when contamination levels are expected to be higher or lower in specific parts of the population, and we want to be sure to sample each of these parts randomly. The third one is a systematic sampling. In this sampling strategy, the samples are taken at regularly spaced intervals. The initial location is chosen at random and subsequent samples are taken at predetermined intervals. In the industry, both simple random sampling and stratified random sampling are commonly utilized sampling methods. Finally, the two remaining inputs are the individual sample mass and the detection method. The individual sample mass is the sample mass taken for sample strategy in grams. The suggested value is 25 grams. However, the user can adjust this value according to the type of produce or intended sampling strategy. The detection method of pathogens has two options, plating and enrichment. The user can select according to the pathogen under study for this sampling simulation. The following video for produce sampling simulation will show you how to use the simulation app and analyze the results for sampling analysis according to a real-life scenario.